ready, and then we'll work on additional.
All right, let's get started. Thank you all for coming. It's very rare these days that we get to be in on the ground floor of some new exciting technology of as great a scope and potential impact as software-defined networking, because this is really a tipping point in the way that networks work. So we're really very fortunate to have Casey and Dan here to talk to us today.
My name is Dan Schmidt, Network Services. I think most of you know who I am. This is Dr. Casey Wang. I'll let you say. Casey and I have worked together a lot on software-defined networking. We've been doing it the last 3 years, something like that. And also, students are here too that work in this field. We've got, I'll let you guys see, Reese, Ben,
Scott.
Aaron, yeah. So these guys are kind of really on the forefront of software-defined networking. And I'm going to talk about what it is. My role is more to try to connect what they're doing to like real production networking, which is what my group is responsible for. So if we ask what is software-defined networking and why should we care, I think the first question that we have to answer is, what is a network? To me, that's a network. So you have a computer that sends and receives packets. Okay, so what is a packet? This is what a packet looks like. First, it's just a block of data that is sent over a physical medium. So that could be wires, that could be radios, that could be fiber optics, could be whatever you come up with. In order to send ones and zeros, signal ones and zeros. You could do with smoke signals for that matter. So the first part of the information is the local source and destination address, and then the network source and destination address, and then TCP, like port 80, you might have heard of that, is defined, and then you have the data. We're asking for a web page. This would be the get/HTTP 1.1. The web server would send back a packet with HTML or whatever. And that connects to what we normally would call a network device, a router or a switch. Make sure I point out that that's really a specialized packet forwarding computer with lots of network interfaces. That's really what that thing is. And the original routers and bridges were in fact faxes or whatever kind of computer just with multiple interfaces. And those computers ran software that knew what to do when packets came in those interfaces and could send them back out. I think a lot of times we've forgotten that that's what these things are, and they're these boxes with lots of ports on them. But this is really what's going on here. Every one of these things, and Joe told me we've got, what, 2,500 or so devices on the Clemson campus that my group is responsible for maintaining. Every single one of these things runs an operating system, and every single one of these things is individually hand configured. This is an operating system. This is Cisco iOS software. You know, it's kind of a Unix-like operating system that they all run. Juniper has Junos. Every vendor has their own, but it is an actual operating system. And they all have these configurations that look something like this, that have just long lists of instructions as far as to what to do. Inside that network, these network devices run protocols to tell each other things like how to get to certain networks, how to get to where certain MAC addresses are, all kinds of stuff configured to make all these things happen. So think about this. Every single one of these things is running its own OS. Every single one of these things is running its own software, and it's its own little island, and we have to set up, this is what networking is. It's setting all this up so that it just works. You guys may remember back in April, it all stopped working. because of a simple problem that cascaded itself into a massive failure of these things to not tell each other the right stuff. So packets no longer were forwarded. So, and then from there, it just continues on like that. And actually, this is the way it really looks in the building. These would be building distribution switches. This would be an access switch in the closet. And then these would be Riggs and Strode core. And that's pretty much an example of what the Clemson looks like. Replicate that, 400 times, and that's what you have. So the network industry today, if we take one of those boxes, this is a network switch. It's got specialized packet forwarding hardware running an operating system, and it's got applications to run on it. People, usually when I say applications on a network device, they're like, applications? Who runs applications on a network device? Well, you got routing applications, management applications, access control applications. All this stuff actually has to run on that box. I can even get on a Cisco and I can do a show process, and you can see all these processes. There's hundreds of processes running on these things. DHCP snooping, routing processes, table managers, all kinds of stuff. You got millions of lines of source code. Every protocol that tells a network how to work is defined in a request for comments or an RFC. There's more than 5,400 of those. If one of you guys decided you wanted to write a new routing protocol, how the heck could you do that? It's impossible, basically. You got lots of complicated hardware, lots of memory. It's bloated, power hungry. Does this sound familiar? We'll sell you one box and everything that runs on top of it. The operating system, the application, everything. Mainframe mentality. It's exactly the same. It is no different. You buy that box right there, just the box is a $50,000 piece. Each one of those line cards is $20,000 to $50,000 each. It's a massive investment to buy that. And then you have to buy the operating system. You have to pay for whatever software you want it to run. You're talking about easily a $200,000 thing that is just it, period. Got any issues with it, you want to change it anyway, you got to go to your sales team and try to convince them that you deserve some feature. So, and the reality is even worse than that. Like Cisco and Juniper and others are always saying, oh yeah, hey, we've got, separate applications. If something goes wrong with the routing process, you can just kill it and restart it. And, yeah, right. No, that stuff is all tied in. The OS is dug into the hardware, and the applications are dug into the operating system. And the reality is if one of these applications crashes, you better just turn that thing off and turn it back on again. It's a mess. That's just the way it is. So who can compete with this? How can any open source thing actually do anything? Closed architecture, well sure, we can just dig down in and grab this one hook we know about in the operating system to do this, rather than do it in any kind of specialized, generalized, way that would allow anything. Now, if you had an idea for an internet protocol, there's your idea, and you could run it through standards bodies, and that would only take about 10 years. And then people everywhere would argue about all the protocols, and it'd be mostly vendor driven, and then finally you'd actually have a network protocol, and by then, 10 years later, the world would be a very different place than the one in which you devised your protocol, and it'd be useless. So it should be no surprise that the internet has essentially not changed since the 70s. We've got better hardware and stuff, but the protocols are still exactly the same. We're still squabbling about whether we're going to start to use IPv6, which was standardized in 1998. You know, that process is, you know, if you're not a Cisco or a Juniper or somebody like that, it ain't happening. You know, consumers, it's not going to happen. Innovation, not really ever going to happen. Lowest common denominator features. You know, you can go rattle chains, and unless you are one of a voice of a lot of people, the vendors are not going to listen to whatever your needs are. You're just going to have to make do with whatever they come out with. So here's our network today. That was what we basically had drawn out. We had every single one of those boxes, specialized packet forwarding hardware, operating system applications, complicated protocols, all telling each one of these independently set up things to do. Some guys at Stanford had an idea, and that was to take the operating system out of there, run the applications we talked about out of there, until you have nothing left but just packet forwarding devices, boxes that contain network interfaces and nothing else. That is what a software-defined network is. Suddenly you don't really care whether this is a Cisco or whether you got it from Walmart or whatever. If it meets the specifications, then it's a packet forwarding device. So the steps that they came up with to do this was, one, you have an open interface to the hardware, a simple API that you can program to. You have one operating system, could be open source, could be, you know, proprietary, could be whatever you want. And then a well-defined API on top of that, so that people who don't want to learn about network operating systems but have ideas for applications to run on the network can do that. Can take it one step farther and add a virtualization layer and have virtualized network operating systems all running on different hardwares, on the same hardware. Imagine this. I mean, imagine if you know, we had one physical network and 15 different network operating systems running on top of that, forwarding packets. You know, research networks, development networks, whatever you want. You know, just running on top of all this. In my mind, that's really where the network industry needs to go. So these slides that I've shown you, mostly I ripped off from Stanford. But I think that I did that only because I think they did the best way of explaining it. But I will tell you, I will explain it from my point of view. This is the way that Dan thinks of it. So a network is composed of lots of these switches. And every device has got a forwarding plane, and that's what moves the traffic through the device. Think of that as, and every device has a control plane. If you think of the forwarding plane as the muscles, and the control plane is the brain, that's basically the way the network works. Lots of brains, lots of muscles, every single one of them independent. Okay, so two problems with that. One is that control plane, like we talked about, is we can configure it, but we can't change it. The other problem is that every device has its own isolated control plane. 2,500 of these things, every single one of them we have to manually configure and deal with. It's frankly a miracle that networks operate at all. I think Scott Schenker from UC Berkeley calls network engineers masters of complexity. And as a network engineer, you don't really think about that until you, like me, that's what I used to do, and now I'm a bureaucrat or something. And so I get to step away from all this, and I'm just like, really? Seriously? We really worried about all of those tiny little details, and somehow miraculously it all works. Those people that do that, they are masters of complexity. That's what they have done, is gotten really good at managing a very complex system. So the result is that networks never evolve they just get more complicated. That's it. When you tell a network engineer that you want to virtualize networks, they're just like, ooh, okay. So cloud computing is coming. What does that mean? It means that networks need to be dynamic things that automatically take you wherever your data is. Oh, your data's in the cloud. Bullshit. You know, I know that a cloud at the end has to get that packet to a destination, okay? And that's my job, or really it's the guys who work with me, that's their job, is to figure out where that destination is, and that doesn't happen dynamically. You can't just pick some damn thing up from a data center in Charleston and move it up here and say, I moved it to a different spot in the cloud. No. How did you get the network moved up there too? How did you handle that? How did you handle all the routing? How did you, what? When you tell a network engineer that you want to do virtual networking, this is what they really want to go do. This is one of my favorite things. If you're not scared, you don't understand. So, what do we do? Well, software-defined networking just takes the control plane out of the individual device. Hardware manufacturers just implement a standard API that allows control of forwarding plane from a separate controller. OpenFlow is the first specification that really does that. So when we say software-defined networking, OpenFlow, a lot of people mean the same thing, but it's software-defined networking is what it is. OpenFlow is an implementation of. And that's the little OpenFlow symbol. So then, to the OpenFlow spec, a vendor makes his hardware OpenFlow compliant, and then you can buy a commercial controller. You can make your own. You can use an open source one. Whatever you want to do. So, heck, why don't we just do that? Let's just turn it on. Well, it's not that simple. One, you could imagine that the vendors are kind of sitting here going, wait a minute. Wait a minute, I kind of like this mainframe world that I live in. At least the Ciscos and the Junipers and the people like that are kind of really dragging their feet and pretending like they're trying to be careful. Really, they're probably pretty scared right about now. With all the little guys are going, yes, 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 this is what we want. Google. Anybody know what kind of network equipment Google runs? I think it's Cisco or Juniper. The answer is nobody's. They buy blank, straight hardware boxes with ports in them. Guess what they do? They write their own operating systems, and guess what? It's all defined in software. And I would about guarantee that, it's probably something that looks a lot like OpenFlow on the backside. The first meeting that I went to at Stanford about this stuff, we were all in an auditorium there pretty early, and we were talking about it, and one guy stood up in the audience, and he was some pretty big wheel from Google, and he said, I'm so-and-so from Google, and I think that this is really the way that the networking industry needs to go, and Google will be supporting this and helping in any way we can. And the room just kind of was like, whoa. This went from being like this cool little research project that we're all going to help on that we kind of think is neat to like, wow, this really is going to be something, I bet. So think about this, though. This puts Clemson in a kind of unique position. What is a nightmare to me and the guys who work with me, we don't want problems. We want smooth running networks. We got other people in this room here that think that problems are cool. It's like, wow, rather than working on some stupid, boring homework thing, we've got a real challenge, something we can really fix. So, and we're a university. We've got these people who understand nightmares and operating networks, and you've got these people who are excited about solving problems. So that's why building a partnership between an IT organization like this one and academics is hugely important. Software-defined networking lays the first foundation that you can really do this. So it's a lever that lets you really engage the two pieces of the university, in my opinion. Years ago, I talked to a computer science professor when I first started as a network engineer, and I said, man, why don't y'all teach any networking classes, like Cisco classes? And he said, well, he said, Dan, it probably will insult you, but really that stuff is like kind of tech school stuff. And I was like, and my feelings were hurt, but he's correct. It was and is essentially a trade. You plumb stuff together, you hook it up to the standards, you do it in the standard way. There's a lot of stuff to know, but there's no frontier. There's nothing academic about it. It's just you hook it up, it's complicated, you've got to be a master of complexity and all that nobody understands unless you actually do that stuff. But still, it is essentially just a trade. There's no frontier. I mean, how could there be? It's all whatever Cisco said it would be or whatever Juniper said it would be. That's it. Now, networking is an academic discipline again. It's something, okay, now if the control plane is suddenly open and we can redefine a network from the ground up, we don't have to use Ethernet, we don't have to use IP, we don't have to use anything. We can do it in any way we want. And we can do it on hardware that exists on campus, national, regional, whatever scales. That's pretty exciting. Okay, Jim Pepin will come in here and talk about writing TCP/IP code. Well, guess what? Back in the day, we had computers that were running network forwarding code on them. So you could just go edit the source code and change the way the stuff looked, but it all hardened up into hardware and kind of became fixed. So when he talks about the good old days, that really was the good old days, and these really were the bad old days because there's no way for anybody to get into networks, and that's why I think, from my point of view, most people when they think of a network, they're like, it's wires and stuff, right? Do y'all do something with that? Is there anything to it? I don't know. I just plug it in at my house. I just plug it in. That's where networks have gone. Yet nobody understands, in my opinion, that that's really where the frontier is, and that's really where things need to start changing. You can't do all this right out at the edge. But if you had an intelligent thing that was the whole piece, it could go on. So what is our strategy at Clemson? We're just going to turn on OpenFlow and just turn it on. I mean, that was kind of, Casey got an opportunity to collaborate with the guys at Stanford, and at the time there was this version of Cisco software that you could put on some of the hardware we had that would implement a OpenFlow API. And the first question was, can we put this on the campus network? And I looked at that and it was like something, it didn't appear to have a whole lot of support behind Cisco, and I was like, well, I'm not sure that we can put that on the production network, but we could build, a test lab that would have a mock-up of a portion of the network. We could do that. And then time went on and Cisco decided that they were actually not going to support the OpenFlow standard. And so then that wasn't even available. But Casey and I started brainstorming, and we came up with some things of what could we do with software-defined networking while the industry is putting itself together, and it is. And Cisco now is really left with no choice but to really implement an OpenFlow implementation. But in the meantime, there's some interesting things we can do. So KC and his guys come to some of my staff's meetings, and the question was, well, what would be a useful application? So they just came in and listened. At the time, we were having some nightmare about Kevin McKenzie and his guys wanted us to be able to magically cause, you know, traffic that they needed to monitor to appear out at monitoring stations somewhere, or the Blackboard guys with their co-radiant system. Co-radiant is a monitoring system that you just, well, what they say is, well, you just have your network people send you all the Blackboard traffic to this box, and then we'll tell you everything the Blackboard does. Done, right? Just tell your network people. Your network people have gone and built this big distributed routed network that carefully gets network traffic exactly where it's going, and we've load balanced the application across 2 different data centers across however many servers now, and you just want us to put this crap on one box somewhere sitting where? You know, in Missouri or something? I don't know. You know, so sure, that's no problem at all. Well, it is a huge problem, and it's a big challenge, and there is a whole industry that's popped up around that. Gigamon is a company that builds these boxes that you send network traffic in, and then you can arbitrarily send that traffic wherever you want it to go, to monitoring devices or whatever. Well, we said, well, you know, Casey's guys said, well, hey, you know, with an OpenFlow switch and an OpenFlow controller, we can send traffic, send data wherever you want. So why don't we use it to build a monitoring network, an out-of-band monitoring network? And so this is where the idea of an OpenFlow data analysis network comes in. And so we have implemented a couple of OpenFlow switches, one at Pool and one out here at ITC, and then we send the aggregated traffic from the Blackboard servers into this OpenFlow switch, and then we can redirect it to co-radiant or to Kevin's security appliances or whatever we want to. This lets us get some experience with OpenFlow. It puts OpenFlow in a space where it's not, you know, if it goes down, I guess the Blackboard people would be kind of mad, but life would go on. You know, data wouldn't stop. So kind of that's our method, is to come up with things we could do with OpenFlow that would not impact the network today while things are maturing. And that is happening pretty rapidly. Casey, you want to add anything?
Well, I think, so basically, this is one of the applications that we have been trying to think, how can we, at the same time, enable this research technology, but which we need the support from the university, but can we make that something at the same time useful to the university? And the only way, just like Dan said, we don't want to work on something that is boring out of the textbook. We want to find something that people are really having challenges. One of the reasons when I come this morning, I thought about this opportunity to talk to everyone here. It's probably not so much about the software-defined networking, what is it, or technically how to do it. We can spend a lot of other time on that, but it's really to find out, answer some questions. So I have a lot of questions, and then I bet you all have a question. What is OpenFlow? Why should we do it? And things like that. So the nice thing, I don't know whether I should just cut in right here.
That's a good place. Yeah.
The question I was having is, Clemson has this nice tradition. We have been very good at coming up with our own solutions to solve our own problems. So from early day, I was heard most of the stories from Dan that there was an era that we transitioned from mainframe and then to Linux. Right? So at that time, there are some brave souls coming up saying, hey, Linux is a new stuff, and then we can do a lot of things with it, and we get it to work. And then once we get it to work, we actually create a reputation of doing that well. And then moving on forward, there's a lot of things I observe from my students. So my students are active in Linux, and then there are students active in voice over IP. So when they are still at Clemson, they write their own code and start to get things working.